Welcome to Spring LIB.
In this exercise, we're going to be using the concepts of orbit velocity and escape velocity. So before actually solving the problem, I'm going to review the topic. So consider that we have a certain body, for example, a planet, it can be planet Earth, and we have an orbit around this planet. Okay, and the distance between the center of the planet and the orbit is what I call r. The orbit velocity for this distance is equal to G here is Newton's gravitational constant times the mass of the planet divided by r. This is the orbit velocity. The escape velocity, on the other hand, is the velocity that's necessary to escape the orbit of a planet, and it's equal to, or actually any body, it can be the velocity necessary to escape the orbit of a star or any body, is equal to the square root of 2gm divided by r. Okay, and what we're also going to need in the exercise is that the mass of the Earth is 5.98 times 10 to the 24 kilograms. We are going to need that the radius of the Earth is 6.38 times 10 to the 6th meters. Okay, so what we have is a satellite that's orbiting, actually a rocket that's orbiting the Earth with an altitude relative to the surface of the Earth of 20 megameters. So that's 20 times 10 to the 6th meters. And we want to know what is the increase in the velocity of the rocket so that it escapes Earth's orbit. So what we need to do first is to realize that the orbit velocity, as I said before, is equal to g times the mass of the Earth divided by the radius of the Earth plus 20 megameters, which I'm going to call just L. That's the distance between the orbit and the center of the Earth. The escape velocity is 2gm divided by r plus L. And we want to calculate the difference in the velocity, which is v minus vo. So this is equal to the square root of 2 minus 1 times the square root of gm r plus L. And now I can just insert the numbers. So this is the square root of 2 minus 1 times, times g, that's 6.67, times 10 to the minus 11 newtons meters squared per kilogram squared, times the mass, and the mass is 5.98 times 10 to the 24th kilograms, divided by the radius of the Earth, that's 6.38 times 10 to the 6th meters, plus 20 megameters, so 20 times 10 to the 6th meters. So delta V is equal to 1,611 meters per second, which I'm going to write as 1.61 times 10 to the 3rd meters per second. So this is the increase in velocity so that the rocket leaves Earth's orbit, which concludes our exercise.